So the Arrhenius definition. This is named after the scientist, Swedish scientist Svante Arrhenius. So his definition, and again, back to that quote, it's not that one or more is more correct, but they're just convenient in different situations. So the Arrhenius definition is an acid is a substance that produces hydrogen ions in aqueous solution. A base is a substance that produces hydroxide ions in aqueous solutions. So by this definition, HCl is an acid because when you put it in water, it produces hydrogen ions. It is a covalent compound. Hydrogen chloride is not an ionic compound. It's a gas in its pure form. But when you put it in water, it ionizes completely. So it forms ions. So in water, the HCl ionizes, and we get hydrogen ions and chloride ions. And so it fits the definition of an Arrhenius acid. Hydrogen ions are very reactive. What is a hydrogen ion? It's a proton. A hydrogen atom is one proton and one electron. You take the electron away, you have a proton. That is just this little itty-bitty, teeny-tiny bit of matter. And I think of hydrogen ions, of protons, as being a little bit like, 3-month-old babies. They do not go out by themselves, right? You don't see 3-month-old babies just going down the sidewalk, right? They're always with an adult, right? So I think of a water molecule as being the adult, and the baby is going to be held by the water molecule. This proton is extremely reactive. It is going to react with anything it comes in contact with. If you are talking about an aqueous solution, what's all over the place? Water molecules. So it's going to react with the water. So it's a proton, and so it has no electrons to share with water. So it's going to form a coordinate covalent bond where both of the electrons come from the oxygen. And so it can come, I think of it as riding piggyback on the water molecule. And so we get this is called the hydronium ion, H3O, and it's got a positive 1 charge. Okay, there are other species that exist. So we should know that happens, but I don't think we're going to run into any of them in this class. So what is sometimes confusing is, as a chemist, I will tend to use hydrogen ion and hydronium ion interchangeably. And just whichever seems more convenient at the time. So a chemist understands that when you say H plus ion, what you've really got is this hydronium ion. We may not be writing it out because we don't care about the water's involvement, but we still know that it's there. Okay? So it'll just go back and forth, whatever strikes the mood, right? Any questions about the hydronium ion? Yeah.
So then that's what's produced when an acid reacts in water?
Yeah.
But it's never just by itself.
Right.
So it's like instantaneously as soon as it
Yeah. So you've got the HCl, it ionizes. This proton, this hydrogen ion, is immediately going to find a water molecule. Yeah. Okay. There aren't hydrogen ions just by themselves. No unaccompanied minors. The Arrhenius definition tells us that sodium hydroxide is a base because when you put sodium hydroxide in water, it produces hydroxide ions, right? Sodium hydroxide is an ionic compound, so we don't say that it ionizes. It already had ions. It dissociates. So it separates into sodium ions and hydroxide ions. And that's this equation down here. Okay, so that's a base. Acids and bases are going to can combine in water. They can combine to form water. So we've got the H plus from the acid and the OH minus from the base. And if those two come together, they form a water molecule. Everybody okay with that? Another definition is the Bronsted-Lowry definition. This is applicable in more situations because the Arrhenius definition only works in aqueous solutions, right? So if you're in a non-aqueous solvent, you can't use that definition. So this definition focuses on transfer of the hydrogen ion, which is a proton. So an acid is a proton donor, a base is a proton acceptor. HCl then is an acid because it donates a proton to water. And so here we have HCl and it's aqueous, there's a water molecule around. What happens when this ionizes is that hydrogen ion gets transferred from the HCl to the water that forms hydronium ion, and we're left with chloride ions floating around. So this more clearly describes what happens to that hydrogen ion. The previous definition can leave us thinking that there's just protons floating around in the water, right? So the donor and the acceptor with the acid and the base, another pair of things that you have to associate. I think of the base as the babysitter. So the acid is handing off the child to the babysitter. The babysitter is accepting the child. So the acid is handing off the proton, and the base is accepting the proton. So this definition works for things like NH3. NH3 is a base, and yet it contains no hydroxide ions. It's a base, though, because it accepts a proton from water. So ammonia, a molecular compound in water, will accept a hydrogen ion from the water, forming ammonium ion and producing hydroxide ion. So it does produce hydroxide ion in solution, but just looking at NH3, it's not obvious at all. What we find is that acids and bases always occur together, because if something's going to donate a proton, there has to be something to accept the proton. And in order to be a base and accept a proton, there has to be someone to donate it, right? If there's no one to donate a proton, you can't be a base. You can't accept a proton. So here we've got HCl and water. And I just said that acids and bases always occur together. So this is the acid, right? It's donating a proton to water. Well, what's the base? Who's accepting the proton? Well, it has to be one of the reactants. Water. So HCl is donating the proton. H2O is accepting the proton. So the HCl is the acid, and the water is acting as the base. Yeah. So here we've got HCl being an acid and this being a base. And then let's look at this reaction up here. The NH3 accepted a proton, so that's the base. And what's the H2O? It's the acid, because it's donating a proton. Yeah?
So would you only be able to see this if you'd have to write out the whole chemical equation to see who accepts the proton?
That's a good question. Do you have to
Like
just
if you just have
write
the
out the
reactants?
chemical equation? You have to be familiar with the chemicals, right? You can't, if you're given a chemical equation like this, without knowing anything about the chemicals, yes, you can identify this is the acid, this is the base, by where the proton goes, where the hydrogen ion goes. But if I just give you two compounds, you need some more knowledge about that before you can really say, is this an acid or a base? Okay. So a substance like water that can act as an acid or a base is said to be amphoteric. So this amph prefix is like amphibian. Amphibians live on the land and in the water, right? Amphoteric, it can do both. It can be an acid and it can be a base. Not all substances do this. So here we've got the Bronsted-Lowry acid-base reaction from the previous slide, ammonia plus water, and now we've just written it backwards. It's an equilibrium, but now we're looking at the former products as our reactants. So ammonium reacting with hydroxide, how does ammonium become ammonia? It donates a proton. Well, if it's donating a proton, what is it being? An acid. And what's the hydroxide being? A base, because it's accepting the proton. Right? So when we did it the other way around, we said this is the base and this is the acid. The base became an acid and the acid became a base. That seems a little trippy, but what's the difference? It's the proton. After you've handed off your proton, then you're in a position where you could take it back again, right? Taking it back, you're acting as a base. The base gets a proton, it accepts it, it behaves as a base, it takes a proton. I'm the babysitter, I got the baby. Well, now I'm in a position where I could hand that proton off to someone else and act as an acid. You okay with that? So we call the reactant and product that are different by a hydrogen ion conjugate acid-base pairs. So a conjugate acid is a base which has demonstrated its baseness and accepted a proton. The base accepts a proton, it becomes the conjugate acid. Conjugate base is an acid that has donated or had its proton removed, and now it is a conjugate base because it can act as a base. So a conjugate acid-base pair is two substances that are related by the transfer of a proton. And so we can look at their formulas, and the difference in the formula is an H+. So here we have NH3, here we have NH4+. The difference in the formula is 1 H+. We identify which is the acid and which is the base by who's got the proton. So here, NH4 has the proton, it's the acid. The NH3 does not have the proton, it's the base. Water can act as an acid or a base. If water acts as an acid and donates a proton, we're left with hydroxide ion, which is the conjugate base of water. Any questions? Identifying these things. So in each of these reactions, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. Now, the definition name, Bronsted-Lowry, is in here. Would you answer this differently if it said the Arrhenius acid? Maybe in some situations you might have a situation where there isn't an Arrhenius acid. But this is not somewhere that I'm going to try to trick you. Okay? So you can just kind of skip over the Bronsted-Lowry part. Identify the acid, the base, the conjugate acid, the conjugate base. The conjugates are going to be in the products. The acid and the base are the things we're starting with. So it's just a matter of perspective. Are you looking at the reaction in this direction? Or are you going to write it backwards? Because then it would switch. So we've got two substances here. And the way we're going to identify which is the acid and which is the base is we're going to look at what they become in the products. So this C5H5N, did it lose an H plus or did it gain an H plus? It gained an H plus. So it accepted a proton. What did it act as? The base. So this is the base. And the water donated the proton. That's where it came from, right? So that's the acid. So on the other side then, we have the conjugate acid and the conjugate base. This was the base. What it turned into is the conjugate acid. So this is the conjugate acid. And hydroxide ion is the conjugate base of H2O. Any questions? Let's look at this one. HNO3 and water. Well, what's the HNO3 doing? it's losing a proton, right? So that makes it an acid. And what's happening to the H2O? It's the base. It's accepting a proton, right? So what's the conjugate base on the other side? The conjugate base. It's the one related to the acid. So this is the conjugate base. And this is the conjugate acid. Any questions? Yeah.
So does it just depend on how the equation is written?
Yes. It just depends on how the equation is written. If you wrote this equation with hydronium ion and nitrate ion as the reactants, and HNO3 and H2O as the products, then I would call this the acid, this is the base, and these would be the conjugates. It's a matter of perspective only. Any questions?